Ladies and gentlemen, this is the third and final video for Section 2, Chapter 1 in your McGraw-Hill Algebra 2 textbook. This section will cover a couple of the things that you need to be able to do coming into Algebra 2. These are the items that will be tested on the I-Step 10 if you have not already taken and passed the test. These will appear on the short answer section of the test. So, the first thing you should be able to do coming in is to examine and potentially justify statements about rational versus irrational numbers. Remember, rational numbers are fractions, and irrational numbers cannot be written as fractions. So pi, root 2, root 3, numbers like that. So the first part says the sum of two rational numbers is always rational. So you have to think about that. Think about what that's saying. If we add two fractions, we will get a fraction. That is a very true statement. Okay, the sum, anytime we add two fractions, we end up with a fraction. Okay, the second statement here says the product of a non-zero rational number and an irrational number must be irrational. So let's look at a couple examples of that. If we have 8 times the square root of 2, that would be the product of a non-zero rational number, 8, and an irrational number, the square root of 2. Well, when we multiply those, we learned in Algebra 1, we can't really do that, so we write it as 8 root 2. Well, 8 root 2, that is irrational. And no matter what example we decide to come up with, say we use a fraction like 1/3 and the irrational number pi, we are going to end up with an irrational number. If we use, really any rational number, say -3, and we multiply that by any irrational number, we are still going to end up with an irrational number. So that statement is also true. These are only a couple of examples of what we could do. We just have to think to ourselves about fractions, about what we know about fractions, in order to answer those questions. There are two other skills you should be coming in with based on rational numbers. The first is you should be able to place a square root on the number line. You should be able to estimate where they fall between what two integers on the number line. So it says between what two whole numbers would the square root of 50 fall on the number line. So here's how we do this. There is a set of numbers out there which are more important for Algebra 2 and even Algebra 1 than other numbers. These numbers should look familiar. These are the perfect squares. Okay, those are the result of squaring our integers. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, etc. These blue numbers are known as the perfect squares, and they are the key to this kind of problem. For instance, the square root of 50, it falls between the square root of 49 and the square root of 64 on the number line, which means 7 and 8, because those are the square roots of 49 and the square root of 64. So we would say the square root of 50 falls between 7 and 8. We can also tell which number it is closer to by looking at the difference between the numbers underneath the square roots. See how this is a difference of 1 and this is a difference of 14? That means we are closer to 7 than we are to 8. Same thing for part B. We take that 125, we go up here to our list and we find where that falls. That falls between 121 and 144, which means it's between 11 and 12. So we would say between 11 and 12, and it is closer to 11 because this is only a difference of 4 and this is a difference of 19. So that's how we do that kind of problem. Next up, and this is the final skill for this section, is how to convert a repeating decimal into a fraction. And your fraction should be reduced. So here are 3 repeating decimals. This is a very simple idea. What we do is we say, okay, 2 digits repeat. So 0.18 repeating is 18 over 2 nines. Then we simplify that. Well, the top and the bottom are both divisible by 9. So that would equal 2 over 11. 0.818 repeating is 2 over 11. Okay, same thing for the next one. We have 3 digits repeating. Which means we take that number, 123, and we write it over 3 nines. And again, we reduce that. Those are both divisible by 3, so we would divide the top and the bottom of that fraction by 3, which would be 41 over 333. Doesn't get any better than that. So on the last one, same idea. We have 4 repeating digits, so 8765 over 9999, 4 nines. 8 plus 7 plus 6 plus 5 shows us that it is not even divisible by 3. So we do not need to check. It should not reduce. That should be our answer for the final problem. That does it for the section 2 notes. See you in section 3.